In our last lecture on bonds, we will talk about bond energy, or the energy that is held in a covalent bond. So we've talked about Lewis structures and exceptions, but we haven't really talked about what the nature of this covalent bond is, other than the fact that it's about sharing electrons. So two atoms come together, they share their electrons, they're covalently bound to each other, but what do we know about the nature of that bond, the nature of that interaction, and how much energy is actually held in that region that binds these two atoms together to form the chemical bond? Well, here's a little review from thermochemistry. So if this is new to you because you haven't recently taken the first quarter of chemistry, then you'll want to review some of this. If you need to brush up on vocabulary or whatnot, just I believe it's chapter 6 of the textbook. So delta H is a thermochemistry term that stands for change in enthalpy. And what it tells you is how much heat is either released to the surroundings or absorbed by the system. And so in a chemical reaction or in a transfer of energy, the system will either take in energy, and that would have a positive delta H, and it could release energy to the surroundings, and that would be a negative delta H. Now, there are ways to determine this experimentally. You may have done in past labs a coffee cup calorimeter experiment where you stack two styrofoam cups and you put some water in there and you heat up an object, and then you drop that hot object into the water and you see how hot the water got. The energy left the object to the water in the cup. You might also have heard of bomb calorimetry. This is when a reaction, like a sample, is burned, and the amount of calories in a piece of food can be detected using that. You can also use Hess's law, which states that if you know the enthalpy for several reactions and you add them up, you can get the overall enthalpy for a reaction. And the last way we can do it is with tabulated standard enthalpies of formation. And we're going to talk about this and do some practice problems in this lecture. But just know that this here is an estimate only. It is an approximation. It will give you a general idea, but it is not exact. So if we do not have any of this, we can use bond energies in these calculations. So when I say bond energy, what do I mean? Well, it is the amount of energy that is required to break a mole of bonds in the gas phase. So we measure these with gaseous atoms, and gaseous molecules, excuse me. So you take a mole of gas and you break all the bonds and calculate how much energy is released overall or absorbed overall. So something to keep in mind is that bond energies are always positive because it costs energy to break a bond, okay? When bonds are formed, that will be negative. So if you were to, for example, when we talked about ionizing sodium and chloride, when the sodium is ionized and the chloride pulls that electron together and they come together, it's not actually the pulling out of the electron of that sodium that gives us the energy, because that costs energy, just like breaking a bond does. So that means that in order to have an overall negative process, you have to have more energy released when the bond's formed than you had when it broke. So again, this is covalent bonds. So we're talking about electrons being shared between two atoms. But in the ionic example, we were moving electrons from single atoms. So it's an analogous process, but it is not the same thing. And I want to again reiterate, bond energies are always positive because it costs energy to break a bond. Well, if you've taken a biology class, or if you took a biology class, even in high school, you probably have heard this phrase, the mitochondria is the powerhouse of the cell. And the mitochondria uses ATP as fuel. ATP is a high energy compound. It has a lot of energy stored in chemical bonds. That's a lazy expression. It doesn't capture the full story. Breaking apart ATP into ADP and a phosphate costs some energy. Breaking this bond costs energy. It's just that forming this new product also gives off energy. So the net is negative, but the bond itself requires an input of energy to break. So when we're talking about the amount of energy required to break 1 mole of bonds in the gas phase, we've got these bond energies here, and I want to point something out. Here you have that CO double bond, and you'll notice that it says 736. And then down here in that asterisk, 799 in carbon dioxide. So right away you can tell that these bond energies are not always consistent. This is an average bond energy. So in general, when you have a carbon-oxygen double bond, it's around 736, but not exactly, unless it's in CO2. The carbon-hydrogen bond is about 414, but in different compounds, it might actually be a different value, and that's because when an atom is bound to other atoms, then the way those electrons are shared, that can change, right? So remember we talked about polar covalent bonds, and we talked about how uneven electrons. So you can imagine that if something is bound to a polar compound, that might change its electron distribution. So these bond energies are averages only, and the bigger the number, the stronger the bond. So what that means is to break apart this, for example, nitrogen, molecular nitrogen, N2, requires an input of 946 kilojoules per mole. So this nitrogen triple bond is, this triple bonded nitrogen molecular compound is very stable. So very rarely is this much energy going to be put into a molecule of nitrogen. So it's kind of great that nitrogen forms up most of our atmosphere and our air because it's very inert. It's not going to react readily because this bond is really hard to break and it's not really going to do much chemically. So we can actually use these bond energies to draw some conclusions about some trends. And so we will look at these here, and you'll notice that the single bond has less energy than the double bond, which has less energy than the triple bond. And so single bonds are easier to break than double, and double are easier to break than triple. So remember in the exceptions to the Lewis model talk, I explained that we have evidence, experimental evidence for some of these Lewis structures, and that is because if you can calculate the bond energies and the bond lengths, that gives you an idea of how much double bond or single bond or triple bond character something has. So if we have what we would predict a carbon-carbon single bond, and it turns out that the bond is about 500, that tells us that it has some double bond character. Now remember that I said these are averages, but that's a huge difference. So if you see something that significantly different, that tells you that there's something else going on and that there's probably a resonance structure involved that has like a double bond or something, because you've seen that giant increase in the bond energy. We can also take a look at these guys here. So hydrofluoric acid, hydrochloric acid, and hydrobromic acid. The bond energy for HF is higher than that for HBr. So let's think for a second about why. What property did we learn about in this unit? What property changes covalent bonds. There is a trend in the periodic table that explains this here, and that trend is electronegativity. So fluorine is much more electronegative, pulling electrons towards itself, and it's smaller. So this HF is a lot harder to break than this HBr. This one's bigger and it's less electronegative. So these bonds are going to be stronger than these bonds. All right. So we can use our understanding of bond energies to explain what goes on in a chemical reaction. So here's an example. Methane gas and chlorine gas reacting to form methylene chloride and a hydrochloric acid. So this is an industrial reaction that happens to produce this. When a reaction happens like this, we have to break bonds. That requires an input of energy, and then bonds are formed, which releases some energy. So step one, break the bonds. So we're starting with methane and chlorine gas, and what happens is we break a bond, so we now have a CH3 and an H, and then we have two Cls, because we had to break those bonds too. Once they're broken apart, they can form the new compound. So now we have our CH3 and H coming, or CH3 and a Cl coming together to form CH3Cl, and our HCl coming together to form HCl here. Okay, so this happens in two steps. You break a bond first, then you form a new one. So let's look at another example here. This is another important reaction in industry. Methane gas and water vapor can be used to form hydrogen. So for example, if you wanted to make a hydrogen fuel cell, this reaction would be really important. So this is showing a structure. So here's our Lewis structure of water and methane here. And here's our Lewis structure of hydrogen gas and our Lewis structure of carbon dioxide. And remember, breaking bonds, it's positive, and forming bonds is negative. So let's look at the bonds we have to break. Well, we have to break 4 of these. So 1, 2, 3, 4. And the bond energy for that is 414 kilojoules. So there's 4 of those. Then we also have to break 4 OH bonds because there's 1, 2, but there's 2 of them. So 3, 4. And if that is 464 kilojoules, we add all that together, and it's 3,512 kilojoules that we have to put into the system to break all these bonds apart. So how much energy do we get back? We have one HH bond here, but there are 4 of them, 4 moles. So we know that we get a negative 4 times 436, which is the bond energy of HH. And then we have this C double bonded oxygen in CO2. So we have to use the correct value. And there are only 2 of those. And now notice how you're not using 4 times the CO bond, right? It is a double bond. So you have to use the double bond energy. So 2 times 799 kilojoules. And that gives us negative 3,300-ish kilojoules. So right away we can tell that if we take this and add this, we are going to get a positive value. And that's what we see, 170 kilojoules. So this entire chemical reaction costs energy. So in other words, this is an endothermic process. It has to absorb energy from the environment in order to happen. So let's think about how this can work to our advantage. So let's look at how ozone and sunscreens work. So our oxygen-oxygen single bond is 142 kilojoules per mole, and the oxygen-oxygen double bond is 498. Turns out that ozone is actually a resonance structure that has kind of like a 1.5 bond between the two. And so UV light actually can break those bonds. So you have your ozone, and then the light happens, zaps the ozone molecule, and they lose an oxygen atom and come together to form a new oxygen molecule. So now you've got, where you had 2 ozone molecules, you now have 3 oxygen molecules. If UV light does this, it doesn't reach you and sunburn your skin. So that is one way in which the ozone layer is protective. So this is called the Chapman cycle, where ozone breaks apart into oxygen and a single oxygen molecule, and then this could actually reform ozone by bonding to a free oxygen molecule. That would be the Chapman cycle. And that is how we keep our ozone layer up here in our atmosphere. And as long as the UV light is being absorbed by the ozone molecules, because remember, in order to break that bond, the energy has to be absorbed from the light. So once the energy is absorbed, then it's no longer considered UV light, right? Because remember from chapter 7 that energy and wavelength are related to each other inversely. And so as the wavelength gets longer, then the energy goes down. So here we have our Mr. Sun, and he's releasing these UVAs, UVBs, and UVCs. So you may have heard of broad spectrum sunscreen. That is sunscreen that works for all bands of UVA, B, and C. So when you are picking a sunscreen, you want sunscreen that works for all of these, but especially the UVA and UVB rays, and you'll see why in just a second. So here we have our sunlight breaking this bond, and now so the UVC is coming up here breaking this bond, but then the UVB has enough energy to actually break bonds in your skin. So this gives you a sunburn. And then the UVA rays are the real bad ones because they don't have enough energy to break bonds, but they can actually penetrate into the skin. And this causes free radicals, which can cause cancer. So this is how the sun actually causes skin cancer, by breaking the bonds inside the body. So if you're getting a tan, you're probably also being exposed to UVA rays, and that's where the cancer can come from. So as I said earlier, you want to have this broad spectrum UVA and UVB rays. And you may have heard of lately reef safe sunscreens. So this compound here, the octinoxate and the oxybenzone, these chemicals are really, really bad for reefs. They're not that great for people either. There's some evidence that they can be hormone disruptors. However, if you go on the internet and ask the internet, is oxybenzone bad for you? You're going to get a huge range of answers depending on what sun product that person is wanting to sell you. So if you ask a maker of mineral sunscreen, they will tell you that it's horrible for you, it causes cancer, and it's a hormone disruptor. If you tell an environmentalist, they'll tell you don't use it because it damages the reefs, which it does, it is true. And then if you ask a chemical manufacturer who makes this, they'll tell you, oh, you know, it's only a moderate risk chemical by the FDA, so it's fine. So you want to be able to be judicious when you're looking for information on the internet, or when you're looking for something kind of controversial like that. Use your good judgment. But one thing that I can point out to you is that you do want something that protects across the spectrum. Because if you're not protecting against UVA rays, you're not really protecting against skin cancer. So you do want something that will protect across the spectrum. So whatever chemicals you decide to use for sunscreen, you do want to make sure it does work in that region. Okay, so one last thing about people trying to sell you stuff on the internet. This is Reef Repair Sunscreen. I actually got this came from that company. And they say Reef Repair sun creams and sunscreen do not contain chemicals, have no parabens, formaldehyde, or titanium dioxide. 100% chemical-free sunscreen. It is simply an all-natural product. So I'm thinking to myself, well, titanium dioxide, that's TiO2. That's two elements, titanium and oxygen. And yeah, that's a chemical. So what in the world is this product if it's not a chemical? It's zinc oxide, a natural mineral. Well, guess what titanium is? So yes, while zinc oxide is a safe and effective sunscreen, it is absolutely still a chemical.